So last class we finished chapter 6, and we started on chapter 7, which is where we're kind of using less math, which is cool. But there's a lot of concepts, and some of the concepts are not going to make sense to us. I prefaced this with us last time a little bit. So we were learning about light, and light has wave behavior. It also has particle behavior. And we were talking about the wave behavior, and waves have properties of wavelength, the distance between adjacent crests, basically how long the waves are. Radio waves have really long waves. Light has much shorter waves, like visible light that we can see has much shorter waves. For visible light, that wavelength also determines color, and there's a cool trick to help us remember that. It requires some previous knowledge, but I think that it's knowledge that most of us should have, and if you don't, this would be a great time to learn it. Another property that goes along with wavelength, which has the lambda symbol, is frequency, which has the symbol nu, which looks like a V, but it's got the little tail in the front. It's not always drawn there, which is confusing, but I usually remember to draw it in. And frequency is the number of cycles or crests, the number of waves, essentially, that pass through a stationary point over a period of time, or in 1 second. If you have a really high frequency, you have to have really short waves for you to get all those waves through that point in the same amount of time. If you've got a really low frequency, you have to have really long wavelengths. So these two properties are inversely related. When one number is really big, the other number is going to be really small. And it also has particle behavior. So photons are our smallest piece of light. 1 unit of light, essentially, you can think of it. One little packet or burst of light. And the amount of energy that that packet has depends on the wavelength and the frequency. The wavelength and the frequency are tied together, and so those are both tied to the energy. High frequency, high energy means short wavelength. You should have those ideas memorized. Okay, looking at a zoom out of our full electromagnetic spectrum, we will go through and talk about each of these sections just individually. And here we've got, again, you should have this memorized, just this general trend. There are ways to work it out with that trick that I'm going to show us later, but it would be a good idea to have these memorized. That long wavelength, we can think of big wavelength. Big, high, long wavelength, large number wavelength, low frequency, low energy, short wavelength or small wavelength. Goes along with high frequency, goes along with high energy. And we've got all of these different regions that we classify electromagnetic radiation, which visible light is just a part of. So visible light just occupies this really small spot part of the entire electromagnetic spectrum. Starting off with our highest energy portion of the electromagnetic spectrum, we have gamma rays, which have this like weird Y-shaped looking thing. For their symbol, that's the gamma symbol. These have the shortest wavelength, so they're also the most energetic. These get produced by the sun and stars. So this is radiation that's just out there in the cosmos, out there outside of our planet's atmosphere. And this is one of the challenges with trying to go to other planets. If they don't have a well-established magnetosphere, if they don't have a well-established atmosphere, these kinds of electromagnetic radiation can make their way to the surface, and these will kill you over time. Gamma rays are really high energy, and you can also get exposed to some of them on Earth, but not the same way that you would if you were on, say, example, Mars. There are also X-rays, and X-rays are convenient because they can pass through many solid substances. X-rays are lower energy than gamma rays. They have a longer wavelength and slightly lower energy. X-rays, of course, are useful for imaging, is probably how we have the most experience with them. If you go to the dentist once or twice a year, hopefully you're getting X-rays when you're in there. And when you get the x-rays, the dental hygienist hopefully comes in and lays like a big lead apron on you. Feels like a weighted blanket and you want to fall asleep. They lay that on you and then they put the little imaging thing in your mouth. They line up their little camera, they go outside the room, they press the button, it beeps, and then they walk back in and they do that a bunch of times. The reason that they walk outside of the room is so that they are not exposed to these x-rays. They didn't used to always do that, and so when they were in the room taking x-rays all day, they were exposed to much higher levels of x-rays, and they would get cancer or tumors, is my understanding. There's also ultraviolet or UV light. UV stands for ultraviolet light. If we had to guess, what color do we think ultraviolet light is next to? It's next to violet light. That's exactly right. So this is right next to violet on the visible spectrum, or from the visible spectrum. So that's awfully convenient. Ultraviolet light, you may know, is one of the things that sunscreen tries to block. So if you're putting on sunscreen, what you're trying to do is you're blocking out this UV light. The UV light can give you a sunburn. It might give you a suntan, depending on what sort of things you got going on in your skin. It's less energetic than x-rays, but it's still damaging because it can give you a sunburn. So when you're putting on sunscreen, you're blocking UV light. When you're putting on sunglasses, you're blocking UV light, hopefully. And this is going to be right next to our visible spectrum with violet light. Visible light, on the other hand, does not damage biological molecules. So seeing pretty colors doesn't hurt your eyes as long as there's not also UV light or some higher energy baked into it. It does cause molecules to rearrange in your eyes, and that results in vision. Here's that little bit of previous information that I'm hoping that we all know. Rainbows. What's the order of color outside to in for a rainbow? What's our most outside color? Red. We've got red for our most outside color. What comes next? Orange. And then yellow. Then green, blue, indigo, and violet, and I don't have two separate colors for that, so I'm going to draw just one violet. The reason that this knowing the order of the rainbow is helpful, if we also know the way that curved lines work, which of these colors is going to have the longest track length? Like if we straightened them all out, which one's going to be the longest line? It's going to be the red. Red has the longest path on the rainbow. And guess what? It also has the longest wavelength. Violet on the inside has the shortest path, so it has the shortest wavelength. This is one, I think, easy way that we can remember our order for wavelength. And then if we also remember that wavelength and energy are inversely related, when one goes up, the other goes down, that would help us remember that red, since it has the longest path, it has the longest wavelength, it's going to be the lowest in energy. Another way that we could remember this is knowing that UV light is right next to violet light. UV light can cause sunburns. That means that it's got a lot of energy. So violet light, because it's next to UV light, has the highest energy. If you're exposed to too much ultraviolet light, you get a sunburn. Sometimes those can get really bad. And then red is furthest away from UV light for visible light, so it's going to have the lowest energy. So these are some convenient, helpful memory tricks for us to remember our order for visible light. The other thing that I'd like to point out is that the colors in the rainbow go in the colors of the rainbow. I know it's very silly. I'll show us why that's important later. Okay, moving on to our next lowest energy level is infrared light. Infrared light, also known as IR light. That's the wrong R. Infrared or IR light. And IR light is the heat that you feel if you put your hands near a hot object, like when we heated up our crucibles. We were trying to see if they were cold. You'd put your hand close to them, and if you could feel that heat coming off, that was infrared light that was being emitted. Any warm object, including human bodies, is going to emit infrared light, and this is one way that night vision technology can sometimes be used to see, quote unquote, see in the dark. This isn't necessarily the best way. It's not really seeing in the dark. Usually it's like sending out a flood of IR light, and then it's got a camera that can detect the infrared light, so it's picking that up. If other people also have infrared lights, they'll see you immediately. So not necessarily the best depending on the context. If you're just looking around in the dark, probably no harm, no foul. Infrared light is not going to, usually at like normal amounts, is not going to cause you serious damage. Infrared light, what color is it next to? Red. I'm pointing it out because it feels obvious, but we probably don't think about it because it feels obvious. This is next to red light. Infrared doesn't cause burns, and it's low energy light. This is also part of the reason that laser pointers are frequently red, because red is lower energy, and so if you accidentally zap somebody in the eye, you're less likely to hurt them. Is this dead? It's not dead. Red laser pointer. In case we forgot what a red laser pointer looks like, I guess. You can get other colors though, and the other colors can often feel a lot brighter. The other nice thing about red is that it's sort of on the edge of our visible spectrum, and because it's low energy, it's not going to be too bright. Green's like right in the sweet spot for our eyes, so it looks really bright even if it's the same strength. Violet laser pointers are really dangerous. Other stuff that you can do with infrared is take photographs. So you can take pictures. If you get an IR camera, that's like a heat camera, essentially. So you can use that for all sorts of fun stuff. One of those things looking at like temperature. So this is an example that came up when I was looking at infrared photographs to put these slides together. So this is an image of the shuttle orbiter Columbia returning to Earth in 1982. So here's the shuttle orbiter Columbia, and then here's the picture that was taken of it. So the left side is just regular picture, the right side is the infrared, and usually the way that these things work is they're color mapped to visible light. So the red spots are going to be the hottest, and the violet is going to be the coldest, and the color gradient in between. And this picture, I think is really cool, was taken by this, the plane in the bottom left. So they had a plane flying around that was taking pictures of other things in the sky, which I think is neat. All right, next up on our electromagnetic spectrum, or EM spectrum, is microwaves. And microwaves, confusingly, if you know what radar stands for, are used for radar. Unconfusingly, very straightforward, they're also used in microwave ovens, which is where you'd expect them to be. There's some bands of microwave that are efficiently absorbed by water, and so if you zap water with those microwaves, it's like turning on water's jam. That's their track, and they're going to start dancing like crazy, and that's what happens in a microwave oven. Radio waves, which you'd expect to be used in radar, which I think are used in radar, are also used for radio, which is also where you'd expect them to be. Cell phones, television, other forms of communication are over radio waves. Unrelated to the class, radar is an acronym. I think it's a lowercase a. Radio detection and ranging. There's also LIDAR and some other sonar, I think is also an acronym. That's why I'm confused about microwaves being used for radar, because it says radio. All right, let's arrange the colors of visible light, just 3 of them, green, red, and blue, in order of increasing, so smallest to biggest, wavelength, frequency, and energy per photon. And I will give you some time to work through this. Remember what we were thinking about ultraviolet light. Remember what we were thinking about the way that the colors are laid out and where they fall on the rainbow, and see if we can come up with the correct answers. Please discuss with your neighbor. All right, we are arranging the colors of visible light, those colors being green, red, and blue. Green, red, and blue, not in that order. In order of increasing wavelength, frequency, energy per photon. What's our shortest wavelength of these 3 colors? Blue. Why do we know it's blue? It's closest to the bottom on our rainbow. I'm going to go copy paste that rainbow from earlier. Bam, rainbow. So blue is the most inside of the tracks. It's got the shortest length if we were to flatten those all out and make them into straight lines. What comes next? Green comes next. And then last but not least, we have red, which is the longest. So red's that outside track. It's going to be the longest wavelength. It's the longest wavelength of visible light, at least. And then for frequency, frequency is the opposite of wavelength, the opposite trend of wavelength, and so we just flip the order. That would be one way that we could come up with this. So we'd have red, we'd have green, we would have blue. Of these colors, blue has the highest frequency, red has the lowest frequency, green has the middlest frequency. For energy per photon, if we're thinking about energy, we might also think about UV light, ultraviolet light, which can burn us. It can be bad for you. And the thing that's closest to UV light is going to be blue light. So blue light is going to have the lowest or the highest energy of these 3? It's going to be the highest energy of these 3 because it's closest to violet. So it turns out for energy per photon, it's going to be the same order. It's also red, green, blue. So that's next to violet, which is close to high energy UV light. Red was the longest color on the rainbow, so that's why it's the longest. Blue is shortest on the rainbow. If I ask you a question on an exam, like I've done many times before through all the semesters of the past, about the order for, or not the order, but the lowest or the highest wavelength, frequency, or energy per photon. If I'm asking you for lowest or highest, and these 3 are your options, what's the one color that you should never pick?
Green.
Green, because it's in the middle. Because it's in the middle, it's never going to be the highest or the lowest. It's always going to be the middlest. So if you're asked a question for the lowest or the highest of anything for any of the visible light colors, you better pick one of the two that's on the outside of the rainbow. Something like red or orange, something like blue or violet. If you pick one in the middle, it's crazy time. So don't do that. Please don't do that. I'm mentioning that because that's happened a lot in the past. So test-taking strategy. Okay, where does light come from? Lots of different sources. One of the places that light comes from is things like neon signs. And neon signs, like this one that says neon, very funny. This neon sign has neon atoms in it. So they take neon, Ne on our periodic table. Let's pull out the laser pointer. Ne on the periodic table. Notice that it's a noble gas. Noble gases are nice because they don't react, they don't explode if you heat them up or put them in a flame. And so neon is very convenient because you can, if you accidentally break the neon sign, it doesn't explode and do more damage that way. So these neon atoms that are inside of the glass tube, you pump them full of electrical energy, and depending on the amount of energy that you give them, different light comes out. And you can make a bunch of different light combinations. You can also do this with other elements. So you can take a mercury lamp, which I believe is this blue one, because it says it's the blue one. You can take mercury and you can also do this, which you wouldn't necessarily expect since mercury is a liquid at room temperature, but if you heat it up, you give it enough energy, it turns that color. A hydrogen lamp, if you pump that full of energy, turns pink. It'll put off a pink wavelength. If you take Chem 1, we do a lab, or at least I do a lab, where we get to look at a couple of different lamps like this, which is kind of cool. And as it turns out, the light that's emitted by hydrogen and by these other elements contains distinct wavelengths specific to hydrogen. So we've got a line here, we've got a line here, we've got a line here, we've got a line here. And those are the 4 lines that show up. So what we're looking at here, if we were looking at white light, over on this very right side, that's our red line, would be red, and then it would be the full color spectrum for the rainbow continuously if it was white light, all the way to the sort of violet-y colors on the left side of the periodic table. Periodic table? Spectrum. But for hydrogen, you put hydrogen only, it's just these 4 bands that you can see for visible light. If you put in something else, like a white light spectrum, or if you put in helium or iron, or if you put in neon, they're going to have different emission spectra, and you can typically just look these up online. They're probably posted. Versus the white light spectrum that is a continuous range of all the different colors. There's no individual bands. Why do we have these individual bands? Why is there just black space where there's not color emitted at those wavelengths? I didn't expect us to have an answer to that, but that would have been cool if somebody knew that. We're going to talk about why there's these bands and why there's different amounts of space and different spacing. Like you can see hydrogen sort of overlaps with helium. The colors aren't exactly right on though. It's a different spacing, different number of lines. Iron's got the most. Some of these areas almost look continuous. So if we look at these emission spectrum, the light that's emitted when you power up these atoms, we get those light colors coming out. So why do the excited atoms only emit light at particular wavelengths? We've got our first model of the atom from Niels Bohr that can explain this for us. So in our Bohr model of the atom, don't get too attached to it because we will be leaving it behind later. So in the Bohr model, we have our nucleus in the center. Our nucleus, as a reminder, is where our protons and our neutrons live. So our 2 massive subatomic particles, all of them live in a little cluster in the center. That's our nucleus. You may have heard of family being referred to as nuclear family, the people you live with, the people that you're closest related to. Same sort of idea. It's this tight-knit people in the middle. And then outside of that, we have orbits. We've got these little tracks, If we think of the nucleus like the sun, then these tracks are like where the planets orbit. So we would be on n equals 3 in that case. So these orbits, starting from n equals 1 and counting up. And these are where electrons can live. So electrons can exist on these orbits, and they kind of rotate around or orbit the nucleus. The way that this model works is that the distance from the nucleus to each of these orbits is a fixed distance. And the fancy word for fixed, quantized. So it's a set distance between our nucleus, where our protons and our neutrons are, and our orbits, where the electrons live. The electrons can race around on these. The orbits are specified by a quantum number. Quantum here is related to quantized. A quantum is like the smallest measurable quantity, if I'm remembering correctly. Or we could also think of it as an energy level. So it's like our energy level number. So if we're talking about n equals 1, we're talking about the innermost track. N equals 2 is outside of that. N equals 3 is outside of that. N equals 4 is outside of that. And it keeps going. You don't have to stop at 4. You can just keep pumping that number up. And in the Bohr model, it is impossible for an electron to exist between orbits in the Bohr model. So this is sort of like if you've played with trains that run on little tracks. If we had like big circles of those trains, you can't put the train in between the tracks and expect it to run in nice, neat circles. It would have to jump to one of the tracks. Our options are only n equals 1, 2, 3, 4, and so on and so forth. Another thing that I'd like to point out to us is that the distance from the nucleus to n equals 1, this should be the biggest distance, n1 to n2. Looks about the same. That's just my fault for making this that way. And then n2 to n equals 3 is a smaller distance, and it gets smaller when you go up one more, and it keeps getting smaller and smaller and smaller. So the spacing between orbits gets smaller as n increases. So hopefully remember I was telling us that we're kind of going away from math for a little bit, but that's not necessarily a good thing because we're dealing with concepts that might be a little confusing. These are some of those kind of confusing concepts. You just kind of have to memorize how the system works. And if you've got questions, Logan would be a great person to ask in his SI sessions from 1 to 3, Tuesday, Thursday. Another thing about these orbits is that the electrons can actually move between these tracks. So when a hydrogen atom absorbs energy, one of the ways that it can do that is it can have an electron let's draw some light. Light hits this electron, and that electron absorbs the energy. It gets bumped up, gets energized, gets excited. Excited is also what we would call it when people have a lot of energy, like children, right? Love to get excited. So our electron gets excited, it jumps up to a higher track level. Those higher track levels are higher energy, and it'll run around and do laps on this track until eventually it decides, I don't have enough energy anymore, I'm going to hop back down to that n equals 1 track. And when it does that, it's lowering its energy. That energy has to go somewhere, and the way that that energy gets emitted is as light. So when our electron relaxes, it calms down again, it emits a photon with that amount of energy that corresponds to that gap. Energy, like mass, is conserved. You can't just poof, get rid of it, or poof, make it. And so when it relaxes, it emits a photon, and that photon has, or quantum, has a certain amount of energy associated with it. And we saw earlier, energy is related to the color of visible light. So the amount of energy that it releases determines the color that's emitted. It's not always one that we can see. So the energy here corresponds to a color. Not necessarily one we can see, but some sort of light. And the light that's emitted by those excited atoms consists of some specific lines. Because these tracks are a fixed distance apart, anytime you jump from a higher track to a lower track, you're going to emit an energy that's associated with or that's paired with that distance. So anytime we jump from n equals 2 to n equals 1, this is always the same distance. It's always the same energy. So the energy from n equals 2 to n equals 1, this applies to all of the other transitions as well, is always the same energy. So it's always the same color. So for hydrogen, we just have one electron in a hydrogen atom, so it can make different jumps. It can jump from 2 to 1, 3 to 1, 3 to 2, 4 to 2, 4 to 3, 4 to 1. Whatever jumps you can imagine, it can do those. It can make those jumps down. As long as you give it enough energy to get to those higher levels, it will eventually fall back down to this inside track, this n equals 1 track for hydrogen. And those lines correspond to those different transitions. So that's why there's specific lines that show up on this emission spectrum. Do we have any questions or confusion so far? It's very normal to be confused about quantum chemistry. Even at the very most basic level, it's still very confusing. Again, I think the Bohr model is really convenient for us because we've got orbits, and we can imagine orbits like where our solar system, the different planets are on those tracks. We're going to get more confusing in a bit, though. Okay, so what's cool about the Bohr model, the great success of the Bohr model, is that it predicts the lines of the hydrogen emission spectrum. So not only can you explain the hydrogen emission spectrum, you can also do the calculations, which we're not going to do, by the way, but we will do in Chem 1. We're not going to do that for this class, but you can predict the lines of the emission spectrum. You can predict how much energy is associated with this jump, how much energy is associated with this jump, how much energy does it take to jump up to that higher level. You can predict all of that. However, the Bohr model failed for literally all of the other elements, assuming that they had more than one electron. You can also do it, I think, with a helium ion. So if you take an electron off of helium, then it works. If you take 2 electrons off of lithium, I think it works for that as well. And so the Bohr model is replaced with a more sophisticated model you might have heard of, the quantum mechanical model. So the quantum mechanical model is what we're going to do now. This is why I told you don't get too attached to the Bohr model, but the Bohr model, a lot of the ideas still transfer over to the quantum mechanical model. All right, our quantum mechanical model. The quantum mechanical model, we saw on an earlier slide that quantum, it's related to the word quantity. So quantum would be like one quanta, which would be like one quantity. And it's like the smallest little tiny bit. So what we're talking about when we're talking about the quantum mechanical model, we're talking about the tiniest little piece. And then the mechanical model is just how does it work? So all that we're talking about with the quantum mechanical model, it sounds scary, and it maybe is, but the quantum mechanical model, we're just asking how do the tiniest little particles behave? What's their behavior? Why do they move the way that they do? And we won't cover it in very much detail because to do quantum mechanics properly, at least, you have to invoke calculus. I'm guessing that most of us haven't taken calculus, and even if we have, there's enough people that haven't taken calculus that it's not worth trying to talk about in that way. So the quantum mechanical model, this is our current model of the atom. It replaced the Bohr model. And what's cool about it is that it tells us that electrons don't behave like particles. This is also part of what's scary about it, because it's nice to think about our electrons orbiting on these little paths, and that's not the reality. It's still helpful in some cases to think about them as orbiting, so I'm still going to talk about it that way, but they actually don't behave like that. So what we're doing is we're upgrading our Bohr orbits. Our Bohr orbits are becoming orbitals. So remember how we had the little tracks on our model, right? Nucleus, concentric circles, n equals 1, n equals 2, NUC dot nucleus. Our orbits are getting upgraded to orbitals instead of nice little neat tracks. I did a terrible job with those circles. We are using probability maps. We're not going to do a lot with the probability maps other than showing you the shapes. So probability maps, we're showing where you're likely to find the electron. It's not always going to be in that spot, but most of the time it's going to be in that spot. This is sort of like if you have a really good friend, W, having really good friends, and somebody asked you, hey, where is really good friend right now? Depending on the level of detail with which you know their schedule, you might be able to say, well, I know that it's a Tuesday in the morning and they've got a class, so they're probably in this room of this building on this campus. I know where they are right now. And most of the time you're probably right, but maybe they have a field trip. Maybe they're not doing class in there. Maybe they have a dental appointment that they didn't tell you about. So there's a chance that they're not there. Probability maps work kind of like that. We know, based on past experience and based on calculus, where the electrons are likely to be. And so we can say, yeah, 90% of the time they're going to be there, but 10% of the time they might just be in any old random place. So that's orbitals. And now we've got some fun quotes from famous minds in physics and quantum mechanics to help reassure us that this is big and scary. So from Niels Bohr, the guy that came up with the Bohr model, we've got anyone who is not shocked by quantum mechanics has not understood it. From Erwin Schrödinger, the guy with the cats in the boxes that are maybe alive or dead, I don't like it, and I'm sorry I ever had anything to do with it. And then from one of the great minds of physics, Richard Feynman, I think I can safely say that nobody understands quantum theory. What's awful about this is that we're not going to understand it. Almost definitely we're not going to understand it. We might memorize it. We might know how to use it. We're not going to understand it. What's great about this is these are three huge names. I think Albert Einstein also had a fun quote about it. But these are three giant names, brilliant minds in the field, and they're also saying this is big and scary and we don't understand it really. So that really lets the pressure off because the big, brilliant, huge minds also don't completely understand it. So there's no pressure on us to really understand it. We just have to know it well enough that we can perform on the exam. That's the bar that we're looking for. And the math calculations for this are beyond the course. We will learn some concepts, and you will have to memorize some terms. If you want a jump scare, go look at the quantum mechanics page on Wikipedia, and it'll feel like you accidentally translated, you set the language to some other thing. Okay, so orbits. We're translating those to orbitals. An orbit's a circular path that shows the electron's motion around the nucleus. Right, this was the concentric circles thing. The electron just flies around in a path. These are nice and predictable. An orbital is a probability map, a shape, we're going to learn some shapes, that shows it's likely found in this zone. So they might look like this, the different colors being different levels of the same shape. There's 4 shapes, or 4 shape families. We're only going to look at 3 of them because the 4th one is big and scary and very confusing. The first 3 are less scary, less confusing. The first 2, I think, are perfectly within our grasp to memorize. What's unfortunate about these is that they're very unpredictable. We're just saying 90% of the time it's in this zone. 99% of the time it's in this zone. We don't know where it is inside that zone, and we can't know certain things about it beyond the scope of the class. The way that we specify these orbitals, these shapes, these probability maps, is with a number and a letter. So we're learning number-letter pairs. The number, we previously were calling the quantum number. Now it's the principal quantum number. It's gotten a promotion. So our principal quantum number, n, it's bolded, that means it's important. N specifies the level of the shell. So when we're thinking about our Bohr model, because that one's easy for us to wrap our minds around, hopefully, the different orbit levels works the same way for a principal quantum number. N equals 1 is our closest number, 2 is outside of that, 3 is outside of that, 4 is outside of that, and those are higher energy as n increases. So energy increases as n increases. N equals 1 is our lowest level, and you can count up as much as you'd like. The letter indicates the subshell. The subshell is also the shape family. And we have 4 letter options. We have S, P, D, and F in that order. So S is our first one, then comes P, then comes D, then comes F. If you have questions or confusions or you're just completely lost along the way, feel free to pause me. Especially if you're watching the recording, because then you can literally pause me, but if you're in person, you can also raise your hand and that will pause me eventually. So again, our orbitals are specified with a number and a letter. Our n is our principal quantum number. Starting from 1, counting up, energy increases as n increases. So 1 is low energy, 2 is higher energy, 3 is higher energy, and so on and so forth. And then the letter indicates the subshell. This is just the shape family that we're working with. And our options are S, P, D, and F, and they show up in that order. Let's look at our lowest energy combination. So the 1s orbital is our lowest energy orbital. 1 is the lowest principal quantum number, the lowest n. S is the first letter, the first shape letter. The X, Y, and Z here are just showing us that this is 3-dimensional. What sort of shape is this? It's a sphere, it's a ball. Sphere is nice because S orbitals, S starts with S, and spherical also starts with S. So S for spherical. And I mentioned that our letter, our subshell, is our shape family. So for S, we just have one shape in that shape family, and that one shape is a sphere, which is awesome. We love that. So we can represent our 1s as a sphere. if we have a hydrogen atom at room temperature, an undisturbed, important hydrogen atom at room temperature, that one electron is going to be in the 1s orbital. That's going to be its default location. We call that the ground state. The ground state is the lowest energy state. So our ground state, there's one ground state. There's only ever one ground state for anything. That's our lowest energy option. So for hydrogen, that's one electron in the 1s orbital. You can add energy into the system to bump it out of the 1s orbital. If we're thinking back to our Bohr model with the concentric circles, the circles that are stacked outside of each other, this is like jumping it from the n equals 1 track on the inside, adding some energy, bumping it up to n equals 2. Eventually, given enough time and no energy input, it'll bounce back to that n equals 1. That's where it's going to stay. That's where it's going to settle. For me, the ground state is my bed at home. That's where I like to go at the end of the day, get my energy back, get zapped by all the rays of the universe, and then I come back and I'm excited and I'm ready to yap for an hour and 25 minutes or however long I do it. The absorption of energy can cause the electron to jump to a higher energy orbital. This is an excited state. There are many possible excited states. And these excited states are unstable. Eventually, you will run out of energy. Eventually, the electron will run out of energy, and it has to return to its ground state until it gets another zap of energy, and then it bounces back out to a higher energy orbit or orbital. Okay, adding on to our n equals 1 with our s subshell, we had just, for n equals 1, it's just got s. So n equals 1 only has 1s. 1s is the only option for n equals 1. When we move on to our n equals 2, so we're thinking about, we're adding out, bumping out to a different orbit, sort of what we're doing. We're moving on to a slightly higher energy area. When we move on to n equals 2, now we have two subshells. Subshells are letters. They indicate the shape family, the type of shapes that we have. So n equals 2 has 2s, and it also has 2p. So we get to access our p subshell, or our p family of shapes. 2s, because it's an s, s stands for sphere. So our 1s is a small sphere, our 2s is a bigger sphere, our 3s is a bigger sphere. So this works really nicely with our orbit model from Niels Bohr. 1s is the small sphere, 2s is bigger, 3s is bigger. What do we think for 4s? Also bigger than our 3s. And this is a trend that continues for all the shapes. How are we feeling about 1s? S for sphere? All right. Our 2p subshell is a little less straightforward. Our 2p subshell contains 3 orbitals. Orbitals are shapes. The subshell is the shape family, or the type of shape. And this is in contrast to 1 orbital in 1s, where we had just one sphere. So S only has one possible shape in it, and that's the sphere. P, the P subshell, has 3 orbitals, or 3 shapes. And those three shapes, since they start with P, P for peanut, or dumbbell shape. So they're all going to have this general shape. They have different labels because they've got different orientations. You don't have to remember the labels. You do need to know how many orbitals we have, and you should generally know what the shape is. So they have this dumbbell or peanut shape. And all of these are going to have the same energy. So we've got the PZ orbital, and this is along the z-axis, which is our vertical axis in this case. The PX orbital is along the x-axis. The PY orbital is along the y-axis. All three of these exist at the same time. So we've got one up, one to the side, and then we've got a third one that's like coming out of the board. So one up, one sideways, one coming out of the board, depending on how you rotate it. So we've got S for sphere, P for peanut, and we've got 3 peanuts. The number of subshells, the number of shape families, the number of letters in a given principal shell, N, is equal to N. So for our first shell, or our first orbit, if we're thinking about our Bohr model, for our first orbit, we have one subshell, one shape family. That one shape family is S because S comes first. That's the rule. So S comes first, so we just have the one sphere. And then we have to bounce out to the next shell. So for our N equals 2, we're thinking about adding out to the second orbit. I'm continuing to use the Bohr model so that we have something that we can hopefully connect these ideas to. Wonky style. So for our N equals 1, we just have S. When we bump out to our shell number 2, a bigger shell, we now have 2 subshells, 2 shapes, 2 letters. Those 2 letters are S and P. So S for sphere, it's the same as our 1S, it's just bigger. And 2P, we've got that PZ, PX, PY, are 3 different peanuts. When we move on to N equals 3, we now have 3 subshells, 3 letters, 3 shape families. The third letter that we add is D, because that's the order. And D we will take a look at when we jump out to N equals 4. The number of subshells that we have is also 4, so the number of letters that we have as options, shape families, is 4. And the fourth one is F, and we're not going to look at F because it's scary. That's my professional opinion. Okay, when we get to N equals 3, we have 3 subshells because N equals 3. And those 3 subshells are S, P, and D. The S and P subshells are just bigger S, sphere, and P, peanut. I can't do dumbbells with my hands. All right, so we just have bigger dumbbell shapes. We've got the vertical one, we've got the sideways one, we've got the in and out one. They're just bigger dumbbells. Bigger dumbbells for higher energy. The D subshell contains 5 d orbitals. So for S, we had 1 S for sphere. For P, we had 3 P for peanuts. It's sort of like a chemistry 12 Days of Christmas. And for D, we had 5. And the way that I remember D, or the way that I recommend remembering D, is double dumbbells. Or you could also remember double peanuts. And then F, can we guess how many shapes we're going to have for F? Engage pattern recognition. 7. We are in fact going to have 7. And F for F, no way I'm looking at that. Or whatever you want to think about it. Here is the d orbitals. Behold, in all of their glory. So we can see for most of these, we've got double dumbbells, or double peanuts, right? Heard you like peanuts? We took a peanut, we added another peanut, right? Overlapping peanuts. The way that these letters work, the D, Y, Z, so Z is the vertical axis, and Y, in this case, is sort of like the sideways axis. And so it's just in the plane of YZ, that two-dimensional surface. You don't have to know these, but I think that it's interesting. So if you're interested in that, here's what it is. DXY is the same thing, but it's flat. It's in the XY plane. DXZ, vertical again, but in the other orientation. And then dx squared minus y squared is along x and y, and dz squared is along z, and then we have a donut. The formal name for that would be a torus. Do we have questions so far, or confusion so far about our different number, letter, shapes? There are more practical applications about these that we will be learning. This is just like we have to talk about the underpinnings. And here's that more practical application showing up just in time. So we are going to use these number-letter pairs to write out electron configurations. An electron configuration is just where are the electrons? What shapes are they in? What principal quantum number? Are they occupying? So we introduce the shapes so that we can talk about where the electrons are living, and we can hopefully in our brains, if we wanted to, if we decide to, we can think about what would that shape look like? How big would it be compared to the other shapes? For hydrogen, how many electrons does hydrogen have? It has one. The way that we know that it has one, hydrogen is our first element. In the top right corner in the periodic table in class, there's that number 1. That number 1 means that it has one proton. It is also going to have a matching number of electrons. So this is a little bit of review. Hydrogen has one proton because of that atomic number, and one electron. For their ground state, it's always the same number. How many electrons does helium have? Helium has 2 electrons. How many does iridium have? 77. I could have picked a funnier number than that. So hopefully we're remembering that's critical to writing out these electron configurations. So for hydrogen, our first orbital, our n number, our lowest n number is 1. And in our n equals 1, we just have the s orbital, the s shape. That's the sphere shape. And we can put into that the 1 electron. There's only 1 electron, so that's all we can put in. So our orbital, 1s, and then up in the top right corner, the number of electrons that we put in there. Now you might be asking yourself, how many electrons can we put in an orbital, Mr. K? And don't worry, we'll answer that question when we get to it. We can also draw out an orbital diagram. This is a picture version of an electron configuration. We will have to do electron configurations and orbital diagrams. So where are the electrons is what we're doing with an electron configuration. How are they laid out? Our orbital diagram is the picture version of where are the electrons, how are they laid out. It provides a little bit more information. For our ground state hydrogen atom, where we have one electron, we write the name hydrogen, or we put just H, and we would put in a box. I am usually lazy. And I'm also usually lazy when it comes to orbital diagrams. And so I will typically just write in the bottom line, and we'll just pretend the rest of the box is there. I encourage you to do the same thing. And then for our one electron, we put in one arrow, and this arrow is pointing up. If up is one of our directions, can we guess what the other option would be? Down. Up and down are the only two options. There's no left, right. Arrows can point up or down. Those are the only two options. In this case, we've drawn it in up. Usually, I think people draw it in up first, but that might just be convention. So if you wanted to be potentially controversial or just wrong, I don't think it's wrong, but you could also draw them in as down arrows if you choose to. The fun thing about the direction of that arrow, this isn't the fun part, but it represents electron spin. So there's a fundamental property that electrons have called spin. And the two options are up and down. And the spin is called up and down. They have up spin and down spin, and I know that makes no sense. Oh yeah, it's got up spin. Down spin. What does that mean? Like if I throw a baseball and I tell you, yeah, it's had a lot of up spin. What? Also, I'm not good at throwing a baseball, so that wouldn't happen. So that the direction that we're drawing in represents the electron spin. The options are up and down. And we were wondering, at least I was wondering for us, how many electrons can we fit into one orbital, into one shape? The answer is 2. We have the Pauli exclusion principle, our first of a couple of rules related to this. The Pauli exclusion principle says that orbitals are the individual shapes so our S for sphere, our PZ, our upright peanut, our standing up peanut, our PX, our PY, each of those can hold 2 electrons. So maxing out at 2 electrons per orbital, per shape, with opposing spins. So if electron number 1 is up, then electron number 2 is down. They have to be offsetting spin, up or down. Let's try writing out electron configurations and orbital diagrams for helium and lithium. To write these, we need to first know something about them. Does anyone know what that something about them is? Number of electrons, that's exactly right. So how many electrons does helium have? He has 2 electrons. He for helium. So helium has 2 electrons because it's got that number of 2 in the top right corner for the periodic table in class. On our yellow sheet, I think it's directly above the symbol. So we start with helium. Our electron configuration tells us where the electrons are going. What's our lowest n number? Principal quantum number. We're thinking about orbits. It's our lowest number. Lowest number is 1, so we're going to start off with 1. What's our shape family that exists in n equals 1? There's only one of them. S. So we're starting off with 1s. What shape is 1s? 1s is a sphere. How many shapes do we have in 1s? We just have one, just one sphere. S is always 1. And since we have one shape is one orbital. One orbital can hold how many electrons? 2. So we put those 2 electrons in 1s, so it's 1s2 would be how we'd read that. That's the electron configuration. For the orbital diagram, time to get lazy, we draw in our one box. That one box is for the one shape that is in 1s. I usually just write under the box or under the group of boxes the number and letter pair. So 1s, we said that we have 2 electrons. What's one of our spin options? Up. I usually draw them in as half arrows. So if our first one's up, what direction's our second one? Down, down to match. So up, down. And that's our complete electron configuration and orbital diagram for helium. Moving on to lithium. Lithium on our periodic table. We're back to the first column, our alkali metals. Lithium has the number what? It's got the number 3. Li has 3 electrons. So we've got our symbol, Li. What's our first N number? It's 1. Still 1. What's our first letter? S. And that's the only one that we have in n equals 1. n equals 1 only has S. How many electrons can we put into this one shape? We can put 2. All right, cool. We used up 2. So we took our 3. We subtracted out the 2. We have 1 remaining electron. Do we have any more subshells? Do we have any more letters in n equals 1? No, we don't. So what do we have to do? Bump out to our next number. So instead of n equals 1, we've got n equals 2. What's our first letter? S. S is our first letter. Can we fit 1 electron into our 2s? We sure can, and we do. Squiggly line our way up. So now instead of just 1s2, we've got 1s2, 2s1. And that would be our electron configuration for lithium. It's always the same pattern. We will learn there's a specific order that the numbers and letters go in. We'll learn where that comes from, a couple of ways to come up with it, and a way to read it off the periodic table even, but that'll be for next class. Now moving on to our orbital diagram. We draw in our box. This box represents 1s. It's helpful to do the electron configuration first, because then you just copy what you did for the electron configuration. So we take our 1s, that's our first box. We've got 2 electrons. We're going to do up and down. They have to be opposite spin, and up and down are our 2 options. Then we've got another box for our 2s, and we've got 1 electron in there. So we can put that in as an up spin electron. Do we have questions about how I came up with those? I would like to point out, again, that this is confusing. And especially like for now, for where we are right now, it's normal to feel confused. You do have to practice doing this so that you get less confused. I'm your weird friend that knows how to play a really specific board game, and I'm really good at it. And I'm telling you that you also have to learn how to play that really weird specific board game for the class. We're just going to take a sneak peek at what's coming next. So in multi-electron atoms, anything that's past hydrogen, the subshells within the principal shell, so our different letters, right? That's what we mean by subshells. We're referring to letters. Those subshells within a principal shell, an n number, do not have the same energy because of the way that the electrons interact. What we're showing on this graph, the y-axis is energy. That's our only axis. We've got separated out our s subshells, our p subshells, and our d subshells. Each of the individual boxes represents each of the individual shapes. So for s, we've got one box because we only have one shape, one sphere. For p, we have three shapes, or three different peanuts. For d, we've got five shapes because that's the next odd number, the double dumbbells, and also the one with the little donut. And we've got them offset just so that it's easier to see the spacing. This is the order that these things show up in. So it's 1s, 2s, 2p, 3s, 3p, and you would think it would be 3d next, but it's actually 4s, then 3d, then 4p, then 5s, then 4d, and so on and so forth, and it gets really fun and confusing. It looks really confusing. There are ways to remember the order. You don't have to memorize this. But this is the order that we would fill them in normally, however many atoms, or however many electrons that we have. So we'll learn more cool, fun stuff about this next class. I recommend that you study the stuff that we covered today so that you remember it next time that we come back in here, because I'm going to assume that we know it.